Welcome to Breadboarding. This is video 11 of the Breadboard video controller series, and in this video what I'm going to be doing is extending the character mode functionality to include high resolution 2-color graphics at 640 by 480 resolution. In the previous video you'll have seen that we used the character based mode to develop a Tetris application, and we used the custom character generator RAM to be able to define special characters for the tetronymos for the game, and also to define the borders for the windows. In this video we're going to be carrying out step 6 of our video controller plan, which is to build the 2-color high-res graphics mode. To do this we're going to be using the two 32K single port video RAMs that we added to the project in the last series of videos. This is very fast, 15 nanosecond access time, and will allow us the amount of RAM we would need to do 640 by 480, which needs about 307,000 bits, which is about 38K of RAM. Now we're going to be using pages of RAM in 16K blocks because that's the way how the video RAM's mapped into the Nanocomp address space. We're going to need to access the video RAM in page 0 and 1 in 16K blocks, and then the page 2 will only need about 5 and a bit K's worth of data in there. We're going to be using 8 bits of the video RAM to directly control the pixels going out to the display, and 80 characters with 8 bits or 8 pixels gives us 640 pixels across, and we also want to do the 480 rows or lines down. However, there are some limitations. So the cathode ray tube controller chip, the CRTC chip, only has memory lines, addressing lines for 16K, and we need a 64K range to do this graphics mode. And also the CRTC has a maximum of 127 total vertical rows, and in fact we don't have quite enough to be able to do 4 raster lines per character. In fact we need 3 bits or 8 lines per raster character. So what this means is to get 480 lines with 8 raster lines per character, we then need 60 characters per screen. Now the Nanocomp video RAM is only 16K in the main address space, and so because we need to map that to 64K, we need to do something about that as well. So we're going to define the character height as 8 raster lines, so that uses the RA0, RA1 and RA2 outputs from the CRTC, and this is normally used to control which is the current raster line of the character generator RAM that we're outputting for the current selected character. But what this does is by using RA0 to RA2, it extends the address range that we can access through the CRTC to give the 64K that we need, and in fact we don't even need the MA13 line in this particular case. And then to address the RAM from the main memory map, then going to add a page register with 2 bits, PA0 and PA1, which we're going to use to map the 64K video RAM into 4 16K pages for the CPU. What I'll just show you is an Excel sheet that I used in the previous videos to look at the character definitions for how we wanted to do the timing and the data and address lines for the character, and I've updated this for the 640 by 480 graphics with 2 color. And what this shows really is that we've got the video RAM 1, which in the previous videos we used as the character RAM, and video RAM 2, which was the color RAM, which we used to determine the colors for the given characters. Now what I've done here is identified for the CPU and the CRTC which line, so we've got the video address lines A0 to A14, so that gives a 32K block in the actual RAM chip. And then from a CPU point of view, all these white lines are fairly straightforward. It's just a 1-to-1 mapping, so 0 to 0, 13 to 13. And then the top address line there, which determines whether you use the lower 16K or the upper 16K, we're going to use the page register bit 0 to determine whether we use the lower or the higher area of that. Then from a CRTC point of view, the first 3 address lines for the video RAM are going to be driven from the raster address outputs from the CRTC, and then the next lines then will be used from MA0 to MA11 will be used to drive the rest of the address lines. Then finally the MA12 line from the CRTC will be used to determine which of the two chips is selected. So you will see here that for the video RAM 1, MA12 equals 0 for that to be selected, and for this one over here we can see that MA12 equals 1 for it to be selected. With the exception of the rules here for the enabling of the video RAMs, we've got PA1 equals 0 here, and we've got PA1 equals 1 here, and MA12 equals 0 and MA12 equals 1. So the configuration for the two RAMs are the same, apart from the output enable and the selection logic will use the PA1 and the MA12 values to determine that. Then the outputs here are shift register A to H, shift register A to H, and those are going to go off to the shift register. And over here, what I have just shown is that we've got our bits on our page register, so PA0 and PA1 just map the 16K block into page 0 is 0 to 16K, 1 is 16 to 32, 2 is 32 to 48, page 3 will do 48 to 64K should we need it. And then of the page register, we've also got two other bits that we're actually going to be using to configure the graphics configuration. Graphics mode bit 0 and graphics mode bit 1, I've called them. And when GM1 is set to 1, it's in graphics mode. When it's in 0, it's in character mode. And in later videos, as we add the 256 colour support, then we'll use the GM0 value to determine if we're in high-res 2 colour or in lower resolution 256 colour. So now just look at how the memory map for this 640 by 480 looks. So because of the way how we've done the raster address lines, then the way how the screen XY coordinates map to the addresses is a little bit unusual. So the start of the video RAM is at 8000 hex, and we can see here we've got the rows down the left hand side. So this is going from pixel row from 0 down to 479. So this is 0 indexed list. So it although it's 480 pixels, it goes from 0 to 479, and then across in the columns, then it goes from 0 all the way up to 639, so that's 640 pixels. Now, because the pixels are arranged in bytes, then in fact the 0 to 7 will in fact be this first byte here, and the most significant bit is on the left hand side and the least significant bit is on the right hand side. So when we're updating the X and Y coordinates of pixels, we need to take that into account. And you can see here that because we're using the raster address for the first 3 bits, that in fact, if we were wanting to update the memory across the screen, we need to, for each subsequent 8 bits or each character slot effectively, we need to add an extra 8 onto each character. And you can see that if we were to write sequentially from 800 downwards, then in fact we'd be writing in 8 character blocks. So if we incremented the value here like we do for the clear screen, and what it's actually doing is clearing the screen starting like that, then going back up to here, going down and sort of working its way through. And what it actually means is that we're effectively treating these group of 8 raster lines of the graphics is effectively treated as one character. And in fact, when you look at this group of 8 lines here, it's in fact 640 bytes or 280 in hex. So you can see here that this is the first row on the screen, and then this is the second row, which is 280. Now what this means is it's a little bit complicated to work out the positions of the X and Y to the address, but this shows here that when we get to the end of the first page, that in fact you can see here around sort of row 200 to 207, so Y value of 200, 207, then we get to the end of the first block of 16K RAM, 16K block, and you can see that is about between 48 and 49. And when we look at the demonstration test programs, we'll see that the first block of patterns will change between character 48 and 49, and similarly when you get to the end of the next page, then in fact that boundary between the sort of the 200 series and the 400 series here we'll see that around character 16, then we'll go from the page 1 test pattern to the page 2 test pattern around that sort of point. So we see that in the test program, and the C code that is going to be used for drawing this includes all the translation of how to go from the row and column addresses here into a specific address, and even to which bit within that particular byte needs to be set. So this just summarizes our page register. So we're using a 74LS octal D flip-flop with clear. So the key thing about this with the clear is it means that when the CPU reset goes low, then it will mean that the values for these will always get reset to 0. So it means that the video RAM will always default to the first page, and in fact this will default to graphics mode on reset or boot up. Now, to ensure that those reset signals are nice and clean, and also to help us in later videos where we want to do better synchronization of the CPU and the video RAM access, then what I'm going to do is to add a microprocessor supervisor and reset circuit. So if you look at this circuit, we can see here that the reset pin has an RC combination here, and this results in approximately about a 250 millisecond reset time. Now, the 6809 CPU is designed specifically that the reset signal will only acknowledge the reset when it goes above about 4 volts, whereas most TTL inputs will count a high value as probably over about 2.2, 2.4 volts. So what this is designed to do is to allow the CPU to reset after all the other peripherals have been reset. But in order to make sure that the CPU and the CRTC are coordinated from their clock point of view, then we're going to make sure this reset signal is a bit more uniform. And what this will do is replace the current resistor capacitor RC combination, which is used on the basic design which came from the 1981 project. One of the things that the microprocessor supervisor circuit does is has a watchdog facility, and what this does is monitors a pin which should be toggled by the CPU when it's working normally, and if that pin is not toggled for a certain period of time, then the supervisor circuit assumes that the CPU's got confused and hung, and so it will reset the CPU. Now, we don't actually want to use that, so all we're going to do is to wire the watchdog pin up to a clock pulse from the CPU, the E-clock signal, and what that will mean is that it will never go into this watchdog process. One of the other things we're going to need to do is to add additional CPU address decoding. So because we're adding the page register, and we also need to address the color latch so we can determine what foreground and background colors we want to use in our graphics mode. And in later videos, we're going to be adding a 256 color video digital analog converter chip. So in order to do that, we need to give ourselves a bit more space for address decoding. So what we're going to do here is to take the CRTC Y3 signal, which currently is in this address range, and what we're going to do is to add an additional address decoder similar to the one that was used on the original Nanocomp, and what this will do is to break the D400 range into 128 byte blocks. So you'll see these are the addresses that we'll actually have here, and in fact to do this we have to change the PLD that does the main address decoding so that the Y3 signal, rather than just referring to this D400 to D4FF range, it will actually cover the whole range down to the D7FF. So this is the original character mode block diagram that we had from the previous video. So it's getting quite busy now, but fundamentally we had the 2 video RAM chips here, which are being driven by the CRTC and the CPU address and data bus. The character generator RAM was used to actually produce the raster output. So this is the bit output that goes to the shift register, and the shift register then determines which bit is determining the foreground and background color through the multiplexer here. In this next stage of the project, we're not going to be using the character RAM anymore, and what we're going to be doing is taking the bit output for the 2 video RAM chips directly out of here through 2 latches and into the shift register over here. This is going to be fed by the raster address lines RA0 to RA2, the computer address lines, and the MA0 to MA12 as we saw previously. Then the page register is going to provide the additional information we need to be able to break the 64K video RAM here down into 16K blocks that the CPU can address. and then the data coming out of each video RAM chip will go through a latch which will then send it out to the shift register. So the logic we'll have is it will disable the character RAM when it's in graphics mode, so this won't be output anything, and then the logic will also then determine which of the two video RAM outputs we need to send to the shift register depending on the address range currently selected. So some of the logic there is going to be quite tricky, and it took me a little while to get it all working properly. So the PLD programming rules were quite complicated, but now that it's all working, it's all fairly straightforward, but it took a little while longer than I thought it would to actually get all this working properly. So what this now then does is that the bit values are coming out of the video RAM here determine if it's a 1 then it shows the foreground colour, if it's a 0 it shows the background colour, and what we're also doing now is adding control signals to the original colour latch here so we can address it via the CPU and we can determine what the foreground and background colours will be. So I'm just going to take you through the main changes on the schematic. So what we've done is added a number of chips. So we've got our additional address decoder here. So this is taking the Y3 signal out of the current PLD address decoder, and it is breaking this down into additional signals. So we've got one going to the CRTC as we had before. So this is the CRTC one, but then we've also got additional signals going off to the new chips. So this is the color latch, so we can update the foreground background color that we use for the image, and then we've also got the page register value here. So this is our address decoder that we've added. We've then got the page register, graphics mode register down here. We've also added two additional latches, so there's a latch here and a latch here. These are now taking the output from the data. So we've got the data lines coming out of the video RAMs here, and this is now feeding the output from the video RAMs into the shift register up here. So this is the shift register A to H values, and we've got two latches here, one for video RAM 1, which is originally we called the character RAM, and the other one is for video RAM 2. We're taking the video signals out from their respective character RAMs and into these latches, and then the output of the latch will then go to the shift register up here. We've also done update to the PLD that we've got here. So this is the video VGA1 PLD, and we've updated this to have a number of additional pins here. So the main changes that we've got are we've changed the clock signal here. The clock signal is now, rather than coming from the dot clock, is now coming from the dot clock divided by 4. So this means that our display enable signal doesn't require so many flip-flops in this PLD to delay. So when the display enable and the display enable out comes out of here, we're able to delay this by the 4 dot clock cycles just using a single a single flip-flop. We've also added the graphics mode 1 and graphics mode 0 input pins and page address 1 bit. Those are required to do the additional address decoding we need for the output. So that's for the graphics 1 and graphics 2 enable signals, which go down to the latches for the graphics 1 and graphics 2 chips. As you can see here, the graphics 1 enable here. So these are the additional control signals needed to control the graphics latches, and we've also added the memory address 12 from the CRTC, which is needed to handle the decoding between the two chips. And finally, we've needed to add an additional signal in here for the Y3 color latch signal, in that in addition to enabling the color latch here, what we also have to do is to enable the data buffer here. The 74LS2045 data buffer here also needs to then be enabled so the CPU signals can get to the color latch. So what this signal does is means that it's been added into the color buffer output signal here, so that when the CPU is trying to write to the color latch here for setting the foreground and background colors for our graphics mode, it can also update the buffer here as well. So those are changes. What I'm going to do now is to go in and look at the board layout and to wiring this up, and then we'll come back and look at the software that we need to drive this. We're first going to install the microprocessor, power supervisor and reset chip. So this chip here, you can see on the schematic, takes the reset button. It's got ground signals, VCC plus 5 volts, and output is the low reset, and we also need to feed in a signal from the microprocessor to prevent it from being reset due to the watchdog timer. And there's also the tolerance here for the voltage, and I think this is set to ground, which is 5% tolerance, so it means if the plus 5 volts goes more than 5% out of tolerance, it will reset the processor. So if we have a look at this, what we need to do is to swap out the current manual push button and the resistor and capacitor RC circuit there. And what we're going to do is to swap it out with this chip here. So it's a fairly small 8-pin chip. You can see there. And if we do this such that the inverted reset actually lines up with this bit here, then in fact we won't have to change too much of the wiring. What we will need to do is obviously wire in the extra pins and things, but it should make things a bit simpler. So just remove the button and the RC combination and the power lines, plug in the chip, put in the plus 5 and the ground lines and the wire also for the tolerance. Now we need to hook in the reset button, so that's coming from the keypad over there. So we've plugged in the reset button input. Now we need to get a clock signal to keep the watchdog circuit alive. So we're just going to put in that part of the circuit. So when I first turned this on, it didn't reset properly, and I went back to the data sheet to see why this could be. And we can see here that although the reset output, so the one that would be reset would be positive, was in fact showing a signal, when I just attach the oscilloscope to the low reset output, which is what we need for the CPU reset, it's an active low open drain. This is the same as open collector. So unless it has a pull-up resistor, then it will never get to 5 volts. And I think this is what was happening. So even when the supervisor circuit here was allowing the CPU to come out of reset, because there wasn't a pull-up resistor, then it was never occurring. So what I've done is I've modified the diagram here to add a pull-up resistor. And now when we run this, we will see that it should now reset properly. So what we're going to look at first here in the logic analyzer, I'm monitoring the power supply line. This is the watchdog timer circuit, the push button input and the active low reset output. Now it's got a pull-up resistor. We should hopefully see value on this. What I'm going to do first of all is just power on the Nanocomp. So this is waiting for the plus 5 signal. So I'm just going to turn on the Nanocomp, and what we'd expect to see here is after a period of time, after power on, that the Nanocomp will come out of reset. So if we put some timing pins on here, what we can see here is when the power comes on at that point in time there at 0, and we can see that the Nanocomp will be in reset state until after about 467 milliseconds, so about a half a second. We can see here as well that in fact that it takes a number of milliseconds for the even for the clock to settle down. So we can see that it's only until about 10 milliseconds that we actually get a clock signal. So this is one of the E or the Q clock signal lines that we've hooked this up to here. So I'm just going to look at the reset button. We're waiting for the reset button to be pressed, and what I'm going to do is to press it multiple times quite quickly, and then I'll also leave a bit of a gap. So So what we can hopefully see here is, well, as pressing the reset button multiple times quite quickly, it doesn't give enough of a gap for it to come out of reset. And then I pressed the reset buttons more slowly, and then we can see that there's the gap of about 0.4 seconds before it comes out of reset. So this shows us that the push button is working the way I expect it to. So you can see here there's a bit of a switch bounce here. So about 200 microseconds switch bounce there. So what this circuit will do is to prevent the switch bounce from causing any problems. So what I've done now is I've disconnected the ST signal, so there's now no longer a clock signal telling the supervisor circuit that the processor is alive. And what I can actually see at the moment is the Nanocomp display keeps on flashing on and off about every second or so, so it's being reset on a regular basis. So what I'm going to do is just quickly press the reset button, and we should be able to see the reset state of the, when I run this and press the reset button, and we should be able to see that the process being reset on a sort of once every second or so by the watchdog supervisor circuit. So you can see here, this is where we press the push button, and then we can see here that approximately every 1.13 seconds, then the watchdog timer, because there's no activity on the SD signal, then it's resetting the CPU. And this is the reason why we've hooked up this signal to one of the clock signals, so it's always alive. And this is just showing that without the ST signal connected over here, it's unplugged, then you can see that the display here is just resetting every second or so. So all I'm going to do now is to plug that signal back in, and we should see that this no longer resets. So the reset circuit's working. It was a little bit more complicated than I anticipated because I didn't realise we needed this pull-up resistor here, but now we've got the pull-up resistor, everything seems to be working fine. So here are the chips. So we've got two latches here for the graphics 1 and graphics 2, and we can see here that we've got the video data on one side, and then we've got the shift register A to H on the others, just to make it a bit easier to hook up. We've got our address decoder here, which is going to break out our current CRTC line into multiple addresses so we can address various latches and things. And then this is our page register. So this is the 273 device, and this has a clear on it that we're hooking up to reset. And then this is a new pin layout that I've got for one of the PLDs. So actually I think the PLD here, and we're repurposing some of the pins, and we're going to be hooking up page register and things like that to this here. So those are the chips that we're going to be using, and I'm just now going to take a look at the board layout and see what we need to do for that. So this is an overview of the video card that we had last time. So what we're going to need to do is, we haven't really got enough space for adding the address decoder up here. So this is the current PLD that does the address decoding. So I was going to put the address decoder in there, followed by the page latch, page register. So this is going to go down here. So we may need to reroute some of these cables, but we're needing to rewire these anyway. And then over here we've got the current color latch and the character latch, and I think if we move this bar here, move this up to there, and then we can fit in the extra latch there, and we can also fit the extra latch in there. And then what we just need to do is to wire in the outputs of those over to the inputs to the shift register here. Now probably the easiest way to do this is to fit a ribbon cable from here over to this side. So again, we'll have another bit of a loose ribbon cable getting in the way, but it's much easier than that, than trying to route 8 wires across the board like that. So that's what we're going to do. What I'm going to do is I'll speed this up. So we take out our breadboard buddy first, and we're going to put in the latch for video RAM 2, wire in the power and the control signals for that. Now we need to bring down the white data bus signals which have come out of the video RAM chip and wire those in. Then we're going to put in the graphics latch for video RAM 1, then wire in the data bus white wires in then for video RAM 1. Now we want to connect the output of the two graphics latches together, and then we'll be connecting that output to the output of the character generator RAM over there, because those outputs are then also connected into the shift register. So that means that our bit coming out of the video RAM goes straight to the shift register for rasterizing the image. So now we're going to put in the page register and also then put in the address decoder in a minute. So we're just wiring in 4 data signals there for the moment. Then we'll put in the address decoder, and this is going to be driven off the CRT3 line. So we're just wiring in the CRT3 enable line there, and then we need these 3 address lines, A7, A8, A9, to then break that address range down further into the 8 subdivisions. Now we're going to plug in the color latch and the page register and the enable signals for the graphics latches. Need to plug in the reset signal there, and now we need to wire in the address lines into the buffer chips down the end there, so we had to take those out before. So this is just wiring in the A0 up to about A13 lines, I think it is. Now we need to move the CRTC address lines down a bit. Now, the first time I did this, I just did the raster address 0 and raster address 1, and in a later edition I needed to add raster address 2. So this is the first iteration of doing the changes, and then you'll see we'll need to move these down another wire a bit later. This was the first programming of the PLD for this VGA PLD. We'll need to modify that again, and now we're going to wire in the various control signals, so our graphics mode, page register values, and first of all plugging in the clock divided by 4, the dot clock divided by 4, taking the enable signals out from there to go to the new graphics latch enables, and then that's just wiring in the page address and the graphics mode values there. So this is moving down the CRTC lines to allow for that extra raster address line there. There we go. So let's just have a look at the PLD rules here, and then we'll compile the PLD definition in WinCUPL, and we'll then burn it into the PLD chips using the EPROM programmer. Now, the main changes we've done here is we're now, rather than driving this chip with the dot clock, I've chosen to use one of the lower frequency clocks. So this one is actually the dot clock divided by 4. And what this allows me to do is to remove some of the flip-flop levels that I needed for the display enable to be delayed by 4 clock cycles. So what happens now is, because this clock is a quarter the speed, we only need 1 flip-flop to delay the display enable in and the display enable out. So this has allowed me to get an extra couple of pins, which we're now going to be using for the graphics 1 enable and graphics 2 enable outputs, which are used to drive some of the graphics control signals that we need for the latches. And we've also added the MA12, the graphics mode 0 and graphics mode 1 input signals, and the page register page address 1 signal as well. So these additional signals allow us to do all the address decoding, and we've also got the color latch Y3 signal coming in that we also need to change some of these output signals on the basis of, if we're addressing the color latch to set the foreground and background colors, we actually need some of these signals also to be enabled, particularly so that the output from the CPU data bus can go through to the color latch. Again, these were some of the things it took a while to get to the bottom of. Now, I won't go through the rules down here in detail, but I found it was easier to invert all of the signals here, so that if it was an active low signal, I put the low part of it actually on the mapping to the pin here. That meant that all of my conditions down here were always +1 logic true to have the thing enabled, and I didn't have to worry about whether I was routing signals between different rules here and worrying about whether they're inverted or not. Now, the rules here are really quite complicated. What we've got is the original. We've got some graphics mode rules, and there's also some rules as well that we'll need for the character mode as well. So you can see the graphics mode 0 is in fact character mode, and graphics mode 2 is our high resolution graphics mode. And some of the rules down here, for example, where we've got the the bidirectional buffer for the color latch, for example, has not only character mode, graphics mode, but it also has when we've got the color latch being addressed as well. And some of the conditions on here were quite tricky to actually get to the bottom of and required quite a lot of analysis with the logic analyzer. I won't bore you with all of that because it took quite a while to get to the bottom of, but at the end of the day, the values here are relatively straightforward to understand. And if you want to have a look at these, you can look on GitHub and see all of the PLD files should you want to. So we're going to use WinCUPL to open that PLD configuration file, check it's okay, and then we'll do the compile. It'll probably crash, yes it has. Now we'll open the XG Pro, open the GED file and program the PLD. Now we'll take the PLD out of the programmer and put it back into the board, trying to put it in the right way around. So this is the assembly language test program. I've taken one of the earlier CRT test programs and I've changed this now for our 2-color graphics. And what this has in it is we start with initializing the CRTC variables. So this is very similar to some of the original logic that I had put into the monitor ROM, but what I was finding, it was easier when setting these graphics modes to define the CRT settings down here. Now the main changes we've got here is we've needed to change the number of total rows, vertical rows, some of the adjust signals, where the vertical sync was, and in particular the number of scan lines per character effectively was changed from 15 down to 7. So this effectively gives us 8 raster lines per character cell. We're initializing the CRTC registers, and then what I'm doing is setting the graphics mode. So we're storing the graphics mode configuration to the page register. Then we're loading up the A and B variables registers with our background colors. And then what we're just doing is a clear screen. So all this does is iterates through the various pages of video RAM. Now for testing, what I've actually done is the first block of video RAM has got 2 alternating rows of dots, so this should give kind of a sort of a mid-grey sort of color, and if you look at it in detail you can see that there's 2 rows of alternating dots offset by each other. They've then got the next block of video RAM will be vertical lines, and then this final block will be a combination of horizontal lines and the alternate dots, so it will give more of a checker pattern. So this was just to allow me to see whether the different blocks of video RAM were actually taking the values. And so once you've done that, it really doesn't do very much else. It just will leave the video card in some sort of state which further test programs and things can be done. So what I'm going to do now is just to compile that and load it down onto the Nanocomp. So let's just compile that. We'll just start the real-term application. Just need to choose the SREC output from the assembler. That's the CRT11 SREC. So I've just turned on the Nanocomp. I'll put it into load mode and send the file. Now if we switch the VGA capture card on, we can see that by default when it powers up now it will set everything to white rather than producing the Nanocomp power on message. I haven't updated the monitor to work with the graphics mode yet, so I'm just going to send the file, and now I'm just going to run the test program. So this is a very basic test program, and I'll just set those patterns that I explained in the source on the screen. So if you just 3, 2, 1. You can see that is quite fast. It's assembly language and it's not waiting for any of the video blanking period. It's not very easy to see the different patterns here. What I have done is I've taken the document camera and put it very close up to a monitor, and it makes it a bit easier to see what the patterns are, so I'll show that in a minute. But basically we got the alternating dots here, then we've got the vertical lines here, and then this is kind of like a crosshatch with solid vertical lines with alternating dots in the middle. So that just gives us an indication that the graphics card is working. And what we can also see is about a third of the way down the screen, you can see that the boundary for where it goes from one block of RAM to the next is about character 48, and the final block for the top page of RAM is down at about 16. And if you remember the memory map Excel sheet, then that showed that the page boundaries for the different 16K pages were going to be about 48 and 16. So that actually agrees. You can see there is a sort of checkerboard type pattern, and that sort of is the alternating AA and 55 hexadecimal, which is basically just alternating ones and zeros shifted one either way. This middle section, or the second page in our video RAM, that's just got the vertical lines. So that's got the same byte, I think 55 repeated all the way down. And you can see here at the boundary of the bottom section, we've got the sort of a checkerboard type pattern, which is basically just a solid white line, and then with the intermittent ones and zeros between it. So there's very basic sort of patterns, but it just goes to show that we've got sort of pixel level graphics here. And what I'm going to do now is to update the demo program to try and draw something a little bit more exciting for the graphics display, just to show that we've got 640 by 480. To produce a more advanced test program, what I did, I was looking for some VGA test examples. In fact, I did come across a site, which I'll put the URL from glenstuff.com, who's designed a number of VGA graphics cards for use with sort of legacy 8-bit type microprocessors and things. And what I have done is I've modified it quite a bit. I've taken some other examples, but I used some of the ideas for doing test images and things actually from this example. So thanks to him for providing that. And basically what this does in the test here is we've got a clear screen written in C code. There's a couple of test plot points. The reason for this was just testing the page boundaries to see whether or not the page boundaries were coming out correctly. I had a problem when I was first doing this in that the last page is actually above 32K. And because of using signed and unsigned variables, then where there were still signed variables, then this actually messed up the addressing of the upper 32K block. So it's something that what I ended up doing is changing the variables to be 32-bit long. It's probably not the most efficient way of doing it, but it worked around the problem. So this is a very basic, inefficient test program written in C. It's certainly quite a bit slower than the assembly language at clearing the screen, but I thought for doing things like line patterns and circles, this allows us to do a little bit more quickly. Now, there are a couple of key things here. That the clear screen is doing the individual blocks of 16K blocks of RAM and then updating the page register. So you can see here we're updating the page register from 0 to 1 and 2. And then within that, we're just going through byte by byte, updating the graphics to be zeros. Now, we could make this more efficient by doing a word at a time, doing 16 bits at a time. I'm sure there's more efficient ways we could do this. In particular, I had some issues with the C compiler, for sometimes complaining when assigning certain things to pointers and things, then I got compiler warnings under some circumstances. So there needs a little bit more work to tidy this up, but fundamentally that's clear on screen. Then there is something based on the original examples of drawing a line pattern. So this draws a number of lines, and we'll show you what that looks like. And drawing a circle pattern, which I added to this, and this just draws concentric circles. Now, what this is doing, there's a couple of other examples left from the earlier examples. What there is in here, though, is there's Bresenham's line algorithm. So this is an efficient way of drawing lines. So between the x0, y0 and x1, y1, this mechanism is slightly different from the example in the original demo version here. This is slightly more efficient version, I think, and doesn't require quite as much code. And then the Bresenham's circle algorithm, again, is a relatively simple way of doing a circle without needing floating point or needing any trig functions. And because the first 45 degrees of curve is fundamentally the same as the other 8 quadrants or 8 octants, I guess we should say, then it's possible that when you've determined what one point is, we can then actually plot the other 8 points. And you'll see when the circles draw, you can see that they're actually drawn sort of 8 points at a time as it appears. So this is a fairly simple test program. It's not very efficient or very fast, but it probably gives a better idea of the capabilities of the graphics card here. So what I'm just going to do is to go into my Ubuntu command line here, and this is actually doing the test test VGA1.c, and I have also used one of the Nanocomp libraries that I did for the Tetris game, in that it had a software interrupt for the return, so it would actually return back to the Nanocomp monitor. So we'll just compile that, and if we now download that to the Nanocomp, this program actually sits at 1000, whereas the other test program sits at 000. So it means the two can actually coexist. So all I'm going to do now is to select our test VGA1.srec. I'm going to put the Nanocomp into load mode, send the file. That's downloaded. So we're just going to switch over to the VGA card so we can see this being captured. So this should be on the VGA capture card. So you can see at the moment we've got the test pattern I had left over, the basic assembly language test program, and now I'm going to do go 1000, and we should see this then draw as we go. So you can see this is quite a bit slower at the clear screen, and you can also see that there's the kind of flicker or the snow artifacts appearing on the page there. Now those little dots in the middle are some of the basic pixels that I had for testing out the paging. So each one of these is its own page, and you can see the two down here. One's on page 1 and the other's on page 2, as I was trying to diagnose the issues with the signed addresses. So you can see this is not particularly fast. There's certainly plenty of scope for speeding this up, but this is one of the reasons why 8-bit microprocessors were not used a lot in the mid to late 80s, just because they weren't quite fast enough for doing the more demanding graphics. They were fine for character mode, but not really up to the job probably for doing even VGA graphics. Remember that VGA graphics came along in about 1988, and at that sort of time then microprocessors were certainly onto 386 sort of 32-bit processors by then, and then the Pentium came along in the early 90s, I think, which was when games like Doom, for example, started to become possible because the processor power was sufficiently fast. But this kind of gives you an idea of the 640 by 480 VGA graphics, so it's a lot better than the standard sort of graphics that you would have got for 8-bit micros at the time. And this is obviously drawing the circles, and you can see they're drawing 8 points at the same time. And there we go. So that's the test pattern that I've done up till now. Thank you for watching. What I will be doing in the next video, I was going to try and get a lunar lander game to run in black and white mode. I don't know how easy that's going to be, but I was going to try and get sort of something like the classic lunar lander to run on here. Should say that the original lunar lander game used vector graphics, which this has not got vector graphics obviously, so we'll have to do that using our line algorithm, and what I'll try and do is to make it run fast enough so we can actually play a half reasonable lunar lander game. So thanks for watching. If you found it interesting, please hit like. If you don't want to miss out on future videos, please hit subscribe.